All right, class. I got another question here, a video solution. Let me try one from chapter 37. It's number 57. And it says here, consider the double slit arrangement shown in figure 3557. And it looks something like this. They've got the double slit arrangement and the screen, so kind of your classical Young's double slit. Okay. And then they got the down the middle piece. And it says this. It says where the slit separation is D, so that's normal. And the distance from the slits to the screen is L. Okay, that's normal. But here's where it changes. A sheet of transparent plastic with an index of refraction N and thickness T is placed over the upper slit. So I'll maybe exaggerate in size, but here is then this slit that is covered. So the top slit is covered. This piece of plastic is transparent. It has a thickness of T, so the light travels through it. It has an index of N. It says, as a result, the central maximum of the interference pattern moves a distance y prime, and then they show in the picture that it has moved upward. And the fact that they tell you it moved and that it moved upward is actually very helpful, because I think you might miss, if you will, that it moved at all. But the fact that they tell you it does move and they tell you it moves up will maybe start the gears turning of why it moved up. Now, maybe I'll start with and draw in a different color what it would have looked like had you not put that piece of plastic there. So if that piece of plastic wasn't there, the light from the top slit and the bottom slit right at the center part would have traveled exactly the same distances, so they would have added up constructively. And we don't really know the number, but we just know because it's the same length, we would get constructive interference. And for the sake of discussion, you can get about 1 million wavelengths in 1 meter. So let's just say that there's about 1 million wavelengths there. Okay, so if it took 1 million from the top and 1 million from the bottom, that's why we get constructive interference. Now again, I'm thinking right now without that piece of plastic there. Now, just to the bottom of it, there would be another bright spot. And same logic to the top, there'd be another bright spot. And again, the reason for that is because when these two beams of light come together, and if it's in phase, you get constructive interference. So I don't know if you can kind of see this with my fingers, maybe like, you know, the tip of my index finger and my pinky are the crests of the wave, and so here's a second one, and if they line up, and if you shift them one wavelength, they still line up, okay? And so that's what goes on here, below or above. I'll just talk about the below one, but the below one, the top one has to travel further than the bottom one. And then, of course, the result of that is one extra wave. And if it's exactly one extra wave, you get constructive interference. So that's why as you move from the center going down the screen, it goes to destructive before it goes back to constructive. And it would happen again. It would go destructive before you get constructive again. And so a little bit further down and also further up, but I want to leave some space for drawing up here. But the top one would be 2 wavelengths longer than the bottom one. But they would still line up, so maybe we would still have 1 million in the bottom one. Well, it's angled, so maybe 1,000,001 here, but then this would be 1,000,003. And so they'd be, again, differ by 2, and you get constructive interference. All right, so to do this problem, you need to understand why you get a double slit pattern or fringe pattern to begin with. So reviewing that, hopefully that will help with this question, because what happens when you put a piece of plastic in here is that the light from the top slit, as it goes through that plastic, it does slow down, but time's not of an issue here. You put it there and there's a delay before you see it, but it's so darn fast. That's really not what's going to happen, and it stays there anyway. So the fact that it slows down is not the big deal. The big deal is that the wavelength gets shorter, and so we learn that the wavelength is reduced by a factor of n when it enters in some kind of transparent material. So what's going to end up happening is this, that, and I'll go back to the center, without the piece of plastic, if there was 1,000,000 wavelengths from the top and the bottom, with that piece of plastic, you would now have more than 1,000,000 across the top and still have the 1,000,000 across the bottom. And so this center point on the screen would act maybe more like this point down here, where the top one had more waves, 1,000,003, and the bottom one had only, well, if we were still back here, the bottom one would still have 1,000,000. In fact, let me just use that number. Let me just say that maybe the size of this was just right, that it actually created 3 more waves than it did without the piece of plastic. So if that's true, then across the top would be 1,000,003, and across the bottom would be 1,000,000. And of course, it would still be a bright spot, but it would be the third bright spot. It wouldn't be the central bright spot. So the central bright spot would be somewhere further up, because the central bright one is where the number of waves is the same. And in this case, because of the piece of plastic, the number of waves is not the actual same physical distance because of that piece. So maybe right here where they say this y prime, they're saying from the upper slit to y prime and from the lower slit to y prime. They're saying that right there is the same number of waves. And you can hopefully then see that because of the plastic here, the waves are shorter, but then because the bottom one's further away, you could get the same number of waves from the top and the bottom one all the way to this point. So this is what would happen, is it would shift up, and as they call this m equals to 0, because m is kind of our integer symbol for representing the difference in the number of waves here. All right, so that's the key physics to it. Now we can actually find it, because what you're really saying here is that the extra number of waves introduced because of this plastic must be equal to the extra number of waves introduced because of the angle change. And so I'll start with I think the easier of the two. Let me do the bottom one, because the whole Young's double slit was kind of based on this, that the bottom one would then travel this extra distance compared to the top one by this d sine theta. And just to review that, we did that by making a little triangle right here and said the physical distance from this top slit to the screen and the edge of that green one here to the screen is the same. So the extra distance, delta, is this right here. And that delta is d sine theta. So if I take that extra distance delta and divide it by lambda, and maybe I should call it lambda naught so that I don't confuse it with the wavelength that's actually when it's in the piece of plastic coming up here. But this would be the extra number of waves as it travels to the screen compared to the top one. Okay, now that has to equal, as I said, the number of extra waves introduced because of the piece of plastic. okay? And to do that, I need to subtract. I need to say, well, how many waves am I getting in this piece of plastic now because it's here compared to what was it getting when that plastic wasn't there and it was just air. And the difference between those is the extra number of wavelengths introduced. All right, so I'm just going to take the plastic, which has a thickness of T, and if I divide it by lambda naught, that right there, that would be the number of waves that would have been in this little space had that piece of plastic not been there. But with that piece of plastic there, the number of waves is actually T minus lambda sub n, this up here. It's actually dividing by a different wavelength. It's a wavelength that you would get when the piece of plastic is there. So if we simplify this, this would be T, and I'll move this equation into here, and then move the lambda upstairs. I'd get this, and then the D over the lambda naught, and I'm going to make that small angle approximation. Sine theta would be this vertical distance up, and technically sine would be divided by the hypotenuse, but the hypotenuse is about L if you're talking about distances that are kind of small going up. So we did that quite a bit. So this would be with the y prime over the L. Okay, and now we need to solve this for y prime. So I would have a lambda naught would cancel off on each side, okay? And then I would have, let's see, I would have the L over D when I move that here. I would also have a common T that can factor out, and then I would have the n minus 1. So there is the equation for how far up it would move. It would, of course, depend upon the thickness of that plastic and the index of that plastic and the geometry.